Brilliant. Hi, Mike. Thank you very much for joining us.
Hi, thank you very much for having me. Can you hear me and see the slide all right?
We can hear you and see the slide very clearly. So I'll hand over to you. Thank you very much for joining us.
Great, thanks. So let me do, I'm going to sort of quickly go through some of the projects that we're working on. The work in my lab is very much focused on embodied intelligence and building capabilities to robots, often mobile systems. We're also looking at manipulation and sensing, but based on the sort of physical properties, and a lot of these systems are really inspired by soft organisms like the octopus here, and how they can improve the ability of the system to interact with humans, achieve versatile manipulation, and interact with a complex environment.
Oh, we seem to have lost
some recent work from the group, and this. Oh, can you still hear me?
Oh, sorry, Josh. Sorry, Mike. Sorry, we lost you for a few seconds now, but you're back now. So let's hopefully the connection gets better.
Okay, great. Sorry about that. So we've been thinking about how soft legs can simplify locomotion, legged locomotion. How a control of stiffness can help in locomotion and manipulation. We've been thinking about very bioinspired swimming with a soft body is achieved by cephalopods. And thinking about how we can generate unique types of adhesion with soft or flexible structures. So one thing that we've been thinking about for a while is soft-legged robots, and how soft legs can inherently handle a variety of terrain. Now, one of the challenges with this approach, as you see here, this is from a few years ago now, is highlighted at the start of this video, where you see all the offboard electronics, valves, microcontrollers, etc., required to actuate such a pneumatic system. And so this inspired us to think about building in some of the intelligence to the body of the robot as well. And this was inspired by some work from very nice work from the Whiteside's lab, where they showed that you could do something like generate a ring oscillator with these bistable soft valves. So building off of this, we looked at how we can use this sort of ring oscillator as like a central pattern generator, essentially for a pneumatic soft-legged robot, and that's what you see here. The gate is not optimized because we essentially used the minimum number of valves in this case, and directly connected the three outputs from a three-element circuit to the legs of this robot. But then we looked at how you can build up more complexity with relatively simple control, essentially to control the direction of oscillation of these legs in order to do something like walk in different directions. And here we're using manual input, but the idea is that the entire system is running off of a single pressure source. So there's no control inputs coming in aside from these valve states that we're switching manually. And then, of course, you can also switch these valve states based on inputs from the environment. So this is a sort of contrived example where we're looking at, we have this antennae sticking out, it detects that we hit the wall, and that changes the state of the oscillator in this robot's brain. Another challenge that we've been thinking about is interacting with natural terrain. So for example, sand, and we have a project with Nick Gravish at UCSD to look at actually digging. And I'm not going to show, we'll have some more results to share about that soon. But just the problem of walking on sand, as this video hopefully motivates, it can be a huge challenge. And so we've been inspired by some work from the Hod Lipson's group that was previously at Cornell, where I actually did my PhD, to look at granular jamming. And essentially, if you pull a vacuum with coffee grounds or any sort of grains in an elastic membrane, you can transition from soft to hard, as you see here. And so Emily Lathrop, a student working with me and Nick Gravish, has been looking at can you use this to improve locomotion on different terrains like leaf litter, rocks, etc., natural terrains, by essentially having a foot be soft when it lands and interacts with this ground, and then becomes stiff when you have to move and push off of it. And this is an initial sort of result in this direction, where we essentially put these granular jamming feet onto the end of a commercially available hexapod, and found that sure enough, if you use active granular jamming to improve locomotion on different types of terrain, we also noticed the effect. Sometimes you get this passive granular jamming just due to the weight of the robot. And so that's something interesting to potentially follow up on there. Dr. Rodolphe, who recently defended, has been also thinking about controlling bending stiffness. And so if you have grains in a membrane, it's really nice for changing the sort of compressive stiffness. But as soon as you bend this kind of, if you had a beam made of grains, as soon as you go to bend it, you're now limited by the stiffness of the membrane. And so Saurabh started thinking about how to model bending stiffness versions. There's other groups have also worked on layer jamming, where you have a number of layers that you stick together and essentially it becomes a thicker beam. But that of course controls bending in about one axis. If you want to do bending about any axis, you can do a sort of linear version of this where you have a fiber jamming actuator. And so this is looking at some of the modeling, very nice modeling work that he did, and also experimental work in showing a fiber jamming actuator as a tool, and potentially that can be used as a haptic device to provide resistance to motion in desired configurations. Okay, sorry, I realize this is sort of rapid fire moving through things here, but another we've been thinking about is inspired jet propulsion. And essentially the idea is that it takes advantage of this added mass effect, where it can essentially, by changing its body shape, reduce the water that it carries along when it's trying to move forward, and then increase the water that moves with it when it's trying to draw water back into its body to minimize the amount that causes it to move backwards or decelerate. And so this is well studied in nature. There's some previous groups that have looked at robotic versions of this, and we thought there was an opportunity for a system that could actually change its frontal area, as well as repeatedly actuate. And there's some nice work from other groups since this work came out, also in this direction. But we looked at it's very simple, essentially a very simple mechanism. We now are working on another iteration of this robot. But the nice thing here is that we can do things like look at the thrust that this robot can generate when it draws in water. It's got a refill period. So obviously this is where I'm saying that the velocity decreases. And then when it expels water, it increases. We looked at things like force measurements, thrust measurements as a function of the diameter of the robot, which is key. You really want to tune the amount of water that you draw in to the amount of water that you let out. And you'll see in these high-speed videos the effects that happen when you those parameters tuned properly. And you can also measure in terms of the thrust. And then if you have a untethered platform, you
Hi, Mike. We seem to have lost you again. Mike, can you hear us at all?
It's probably my internet's fault. So
No.
Let me try it again. And if it gets stuck again or something, you feel free to move on.
Let's give it a go. That sounds great.
Okay.
So we've just got onto the, propulsion. Yeah. Thank you.
So maybe I cut out sooner than I expected, but let me just, so I don't run out of time, I'll just talk about this last project. This was a project where we looked at this interesting phenomenon of vibration-based adhesion, and it was actually Mike Everman, who is the father of a UCSD student who's on the basketball team, came and visited the lab, and he said, "Hey, have you ever looked into this interesting effect that happens when you vibrate a plate near a surface?" And there's some very interesting fluid dynamics that lead to an adhesive effect that's controllable, as you see here. So basically, we just have this little eccentric mass vibrator, and vibrating a disc, and you can all of a sudden get a sort of 14-gram disc that supports up to half a kilogram. And the effect is you're essentially generating a very thin layer, like 30 microns roughly of low pressure air. But the truth is, we don't understand all the details of these fluid dynamics, and we're working with some fluid dynamicists in the department to look at this. But it's certainly, if you have a fixed vibration motor, you're going to get a maximum load that's a function of the vibration frequency as well as the size of the disc that you use. And the interesting thing for robotics is that this adhesion, unlike most adhesion, is sort of purely normal. There's very low resistance to motion along the surface because you have this lubricated fluid layer. It's not actually touching the surface, it's sort of hovering right off of it. And so unlike something like Coulomb friction or these sort of gecko adhesives, you really get this purely normal adhesion. And this allows us to do something like design a mobile platform so this is, sort of getting away from bioinspired perhaps, but we have this mobile platform now where we can stick to flat surfaces with this disc and then have a sort of suspension connected to wheels so you can actually apply a normal force. And if you design these things carefully, you can not only do inverted surfaces as we just showed, but you can actually climb up walls as well if you have sufficient normal force to generate traction. And so, we have demonstrations here of driving up a wall around a tube and sort of lifting heavier weights, which are full soda cans. So the downside of this is it's vibrating at acoustic frequencies. So it's not the most sort of pleasant thing to have going on in the background, but there may be ways to think about compensating for that. Okay, so that was the last project I wanted to mention, but thank you very much for your attention and your patience with the connection issues. We have a number of collaborators on the project I talked about here, as well as various sources of funding. But most importantly, I just wanted to highlight the students and now doctors who did the research that I highlighted today: Dr. Dylan Drotman, Emily Lathrop, Dr. Sarab Jadhav, Dr. Will Hicks-Weston-Dox, and Dr. Caleb Christensen. So thank you very much. And if anything was unclear or didn't come through, I'm happy to address in the questions.
Many thanks, Mike. It's good for you to finish the talk. A very brief question. I just wondered, you presented some bioinspired approaches and some kind of more inorganic or non-bioinspired. I think touching back to actually Josh's answer, do you think there is a discontinuity, or do you think if we look closely enough, perhaps, for example, this vibration or some other effects, we can have a route back to bioinspiration, or do you think they're divergent approaches?
Well, I mean, it's all constrained by physics, right? So at some point, I think there's things that are easier for biology to evolve, like, let's say, hairy gecko toes. And there's some things that might be more difficult, like very smooth, flat discs with little vibration sources. And so, we don't want to we are largely looking to biology for inspiration, but we don't want to fully constrain ourselves. And I think the important thing is, in either case, if you can identify the principles that are at play, for example, for adhesion, then I think that's what you want to build into a robotic system. I mean, it's also interesting to do biomimetic research, like maybe the cephalopod project is a little bit more biomimetic in the sense of trying to do the same kind of motion for the sort of understanding what's going on. But I think if you want to, ultimately, if the goal is to build a functional robotic system, it shouldn't really matter if you take the exact same approach as biology. So I guess it comes down to what your goal is, if it's understanding biology or solving a problem.
Thank you very much for that answer. And thank you once again for your talk.